Hello everyone. In this video, we'll discuss about electric field due to extended bodies. This is a part of electric charge and fields chapter. So in this, first we'll discuss about electric field due to infinitely long charged wire. Electric field due to infinitely long charged wire. Suppose if they gave like this, lambda is the linear charge density. Linear charge density of the wire. So infinitely long wire means we don't know its initial point as well as final point. From this wire, they are asking to find field at a point P, which is at a distance R. Here, we'll construct a Gaussian surface. This Gaussian surface, let its length be L and its radius is R. So, as the electric field, I am assuming it is a positively charged wire, so that electric field is radially outwards. So, for that curved surface area points, electric field and curved surface area are parallel to each other. But for that end caps, electric field vector and area vector are perpendicular to each other. So first, if I know about charge enclosed, the charge enclosed will be equal to lambda into L. If L is that length of that cylinder, then from our Gauss law, integration of E bar dot ds bar will be equal to Q enclosed by epsilon naught or E into 2 pi RL, because curved surface area of the cylinder is 2 pi RL, to lambda into L by epsilon naught. L gets cancelled. So electric field will be equal to lambda by 2 pi epsilon naught R. Or else you can write the same equation as by multiplying numerator and denominator with 2. You will get that electric field as 2 lambda by 4 pi epsilon naught R, or that will be equal to 2k lambda by R. So both the equations are important. Here we are having one interesting example based on this. I will discuss that example. So if suppose there is an infinitely long wire and a negatively charged particle, suppose an electron, is revolving around this in a circular orbit of radius r under the influence of this electrostatic force. Find velocity of the electron, that is orbiting around this wire. So then electrostatic force will provide necessary centripetal force. Here electrostatic force means Q into field. Centripetal force will be mv square by r, or else Q into that electrostatic field is 2k lambda by r is equal to mv square by r. So r gets cancelled. So from this, v square will be equal to 2kq lambda by m, or v will be equal to square root of 2kq lambda by m, or else you can write like this, k value is 1 by 4 pi epsilon naught. So square root of q lambda by 2 pi epsilon naught m, both are valid. And similarly, if they ask for angular velocity, then you can use the same equation with mr omega square, or else from the same they may ask you about time period, then mr into omega square is nothing but 2 pi by t whole square. So you can just find time period by comparing with QE, or you can find angular velocity by comparing with QE, or else just like this, they may ask you to find velocity. So very, very interesting example, an important example. And after this, we are having few note points like this. If you are given a semi-infinitely long wire, semi-infinitely long wire, then semi-infinitely long wire means we know its initial point, but we don't know its final point. So from one end of the wire, if suppose they ask at a point P, if I am assuming that as a positively charged one, it will have both x component as well as y component. So it will be directed away. Y component will be k lambda by r, and x component will also be k lambda by r due to an infinite, semi-infinitely long charged wire. And similarly, if you are asked for finite wire, or a finite wire, we'll have two different cases here. They may ask you at an axial point and at an equatorial point. At an axial point means if suppose you are given a wire of length L and let its charge be Q, so that lambda will be equal to Q by L. Now, from one end of this wire, we are considering a point P, which is at a distance R. Then, if I will consider a small element, for this small element, let this element is at a distance of x, that point, and this is dx. Charge associated with that small element will be equal to lambda into dx. And then, if they ask for field due to that small element, field will be equal to k dq by x square, or from this k by x square into lambda dx. So what is electric field means k lambda are constants, integration of 1 by x square dx. So closest point is at a distance of r and farthest point will be at a distance of r plus l. So we can write like this: k lambda integration of 1 by x square minus 1 by x, and the integration limits are from r to r plus l. So from this it will be k lambda into 1 by r minus 1 by r plus l. Here k value is 1 by 4 pi epsilon naught. So this kind of questions we can expect at an axial point. At an equatorial point, if they ask, if you are given a wire like this, if you are considering a point P, this point P is at a distance r and one end is making an angle theta 1 and the other end is making an angle theta 2 with the wire, then electric field at that particular point, that x component will be equal to k lambda by r into sine theta 1 plus sine theta 2, and y component will be equal to k lambda by r into cos theta 1 minus cos theta 2. So this is about x component and y component. And if suppose they ask it like this, if theta 1 is equal to theta 2, then y component will be equal to 0 and we'll have x component only. That x component will be equal to k lambda by r into 2 sine theta Here, if it is exactly perpendicular bisector point, then this will be R, this length will be L by 2. So if they asked us to find sine theta, so as this angle is theta, sine theta will be equal to adjacent side, opposite side by hypotenuse, L by 2 by square root of L square by 4 plus R square, or this will be equal to L by 2 by square root of L square plus 4R square by 2, or that will be equal to L by square root of L square plus 4R square. So we can use this sine theta term over here, and hence we can find net electric field if both the ends are making the same angle. If they are making different angle, then we have to take this as the formula. So these are the few note points. You can expect some questions based on this. And next we'll have electric field due to a charged arc. Electric field due to a charged arc. Suppose if you are given like this, there is any arc, its radius is r and its charge is q, and it is making an angle phi at the center. So its radius is r. Now, if I will not derive that here, we'll take that equation, so that if this angle is phi by 2, definitely this angle will also be phi by 2. So if we consider a small element over here, due to that element, if the field is outward, we will have similar kind of element here also. Due to that also the field will be outward. So that net x components, this is phi by 2, this will also be phi by 2. And this will also be phi by 2, so that we have to integrate that x components. The derivation is not that much important here, but that electric field at the origin or at that point P is given as 2kq by phi r square into sine phi by 2, and the same equation even we can write like this 2kq. This is one format. Sometimes they may ask you in terms of lambda. I'll write that format also. Phi r into r into sine phi by 2. So that charge per unit length, here length is nothing but arc length. Arc length will be equal to angle into radius. So that charge per unit length, it will be lambda. So 2k lambda by r into sine phi by 2. So this is in terms of linear charge density, and this is in terms of charge and angle subtended by that arc. Both the equations are important. Just look at this example. If suppose they ask like this, if it is a semicircle, so simple points like this. If it is a semicircle, or else first I'll discuss with respect to quarter circle. If it is a quarter circle, for quarter circle, angle subtended will be 90 degrees. So that electric field will be equal to 2k lambda by r into sine 45, which is 1 by root 2. So that we'll get that electric field will be root 2 k lambda by r. If suppose they gave a semicircle, then phi will be equal to 180 degrees, or we can write even in radians also pi by 2, and this will be pi. So electric field will be equal to 2k lambda by r into sine 90. What is sine 90 means? It will be 0. So that this will, sine 90 is 1. So it will be 2k lambda by r. And if suppose they gave a 3/4 circle, then phi will be equal to 270 degrees. So 5 by 2 will be equal to 135 degrees. So sine 5 by 2, which is nothing but sine 90 plus 45, which is cos 45, which is 1 by root 2 only. So that electric field will be root 2 k lambda by r if it is a 3/4 circle. This kind of questions you can expect. Or one more example I'll give like this. If suppose you are given there is a quarter circle which is positively charged, this is positively charged, and there is another quarter circle which is negatively charged. Both are having same charge density. So due to positive charge, the field will be directed away. Due to negative charge, the field will be directed inward. And if suppose I'll assume this as E2 and this as E1, so this angle will be 45 degrees. This angle will also be 45 degrees. So those two are inclined at an angle of 90 degrees. What is their resultant? E1 and E2 magnitude wise they are same. It will be root 2 k lambda by r. An angle between them is 90 degrees. So that E net will be equal to 2E1 cos theta by 2. This is from our parallelogram law of vectors. That will be 2E1 is root 2 k lambda by r into cos 45. Cos 45 is 1 by root 2. You will get 2 k lambda by r. So these kind of questions also we can expect, and direction will be along x-axis like this. So this kind of questions also we can expect. And with semi-infinitely long wire and this arcs, we are having some interesting models. I'll explain that examples. Just look at this. They'll give you like this. There is one infinitely long wire is there. It was bent such that at the bend point, we are observing a quarter circle. Suppose this point is a quarter circle, its radius is r. So what is net electric field at this point if they ask? I can divide this into three parts. Let this be first part, second part, and third part. Due to first part, we will have x component like this and y component like this. Due to this third part, we will have x component and y component like this. All they are magnitude wise same. So this x component due to first part gets cancelled with x component due to third part. Y component due to first part gets cancelled with y component due to third part. So that electric field will be only due to this quarter circle that will be in this direction. E2 will be equal to, just now as we solved, we'll get that as root 2 k lambda by r. So this kind of questions you can expect. And similarly, just look at this one more example. If we are having an infinitely long wire, it was bent such that at the end we are observing a semicircle like this. So what is electric field at this point? They will ask. At the center, this distance is r, this distance is also r. Just look at this. I can divide this into three parts. One, this is third part, this is second part. And for first part, we'll have x component as well as y component like this. For third part, we'll have x component and y component like this, so that their y components gets added up. And due to this semicircle, E2 will be in the downward direction. So we know that net y component along positive y axis will be equal to x components. Obviously, they get cancelled, and net field along positive y axis will be equal to 2 of ey components due to two semi infinitely long wires. So that it will be 2 k lambda by r, and along negative y-axis we are having due to semicircle. Due to semicircle also we'll get 2 k lambda by r. So that net electric field at the center will be 0. So this kind of questions also we can expect in our NEET level as well as in JEE also. So next we'll discuss about Electric field due to a charged ring. Electric field due to a charged ring. So in this we'll have two cases. First one is at the center of the ring. So if suppose you are given like this, there is a ring whose radius is r, its radius is r and its charge is q. Now electric field at the center of the ring, can we say like this? We can treat this as an arc. That arc is subtending an angle of 360 degrees, so that 5 by 2 it will be 180 degrees. So sine 180 it will be 0. So electric field at the center will be 0. And we can give one more explanation like this. If you are having a small element on this ring, diametrically oppositely will have another identical small element. If its width is W, its width will also be the same W. Both will produce an equal and opposite amount of field, so that net field will be 0. So that this is about electric field at the center of a ring. So here we are having one interesting example. If the ring is having small cut, if the ring is having small cut, if they ask it like this, so it is not a continuous ring, there is a small gap is there. So if you are given like this, there is a ring with a small gap. Now what is electric field at the center means it will not be 0, because if we will consider a small point exactly opposite side, due to this small element there will be some electric field at the center. So that for this we will find linear charge density, that will be charge per unit length if r is the radius, q by 2 pi r. And now charge associated with that small element will be equal to lambda into w, because that element width is w. So it will be q by 2 pi r into w. Now electric field due to that small element will be equal to k q dash by distance square, or that will be equal to k by r square into q by 2 pi r into w, or that will be equal to k q by 2 pi r cube into w. This is electric field at the center of a ring with a small cut. Small cut means here we have to ignore w with respect to r. So this kind of questions you can expect. Now we are having that second case at an axial point. At an axial point of the ring, at an axial point of the ring, suppose if you are given like this, there is a ring, at the center it is 0. From the center they will give you a point which is at a distance x. So for this distance, radius of the ring is r. Electric field at this point is given as k q x by x square plus r square whole power of 3 by 2. The derivation is not at all that much important for NEET level as well as JEE level, but that final expression is very important. Now, if you remember this equation, they will ask you two things. At x is equal to 0, electric field will be 0 because at the center. At x is equal to infinity also, electric field will be 0 as it is very far point. So that means we can say like this, as it is at 0, at the center it is 0 as well as at infinity it is 0, means from the center of the ring as we move away, electric field is gradually increasing and then decreasing. At what distance it will have maximum value, they will ask. So this is E maximum point. At what distance we can observe this maximum value, they will ask. For this, we have to differentiate this equation with respect to x, because they are speaking about maximum value of E. E maximum means dE by dx must be equal to 0. So we can take that kq outside and take towards right side. So we'll have d by dx of ex by x square plus r square whole power of 3 by 2. This will be equal to 0. So now if you will differentiate this, you will get x is equal to r by root 2. At this distance, electric field becomes maximum on both sides. And now what is that maximum value if they ask? What is our electric field formula? K Q x by r square plus x square whole power of 3 by 2. So that this will be equal to kq into x is r by root 2 by r square plus r square by 2 whole power of 3 by 2. I can write like this: kq by root 2 r square. I will bring outside, it becomes r cube, r and r gets cancelled. We left with r square into 3 by 2 whole power of 3 by 2. We can write 3 by 2 whole power of 3 by 2 as 3 root 3 by 2 root 2. So if you will substitute and solve all those values, we'll get 2kq by 3 root 3 r square, where k value is 1 by 4 pi epsilon naught. So 2q by 3 root 3 into 4 pi epsilon naught r. So they may ask you in terms of k value also. This kind of questions you can expect. And we'll have one more point here. If x is very small, then electric field becomes like this: k q x by r square whole power of 3 by 2 means r cube. For small values of x, x will be very small compared to r. So based on this also, we are having one interesting example. I'll discuss that example here. Just look at this example. There is a charged ring, and at the center, if it is positively charged, I am assuming, and a negatively charged particle is slightly displaced by a distance x, then definitely it will experience an attractive force. It will move towards the center, and again due to inertia it will move towards the other side, and again it will move towards the center, so that this negatively charged particle at the center performs simple harmonic motion if it was given a small displacement. So now our idea is to find what is time period of that oscillation. For that, what is force acting on that negatively charged particle means if its charge is q and this ring charge is q, so we'll have q into E, that will be equal to k q q x by r cube. We can write as mass into acceleration. So acceleration will be equal to k q q by m r cube into x, or that will be equal to, I can write in terms of epsilon naught also, 4 pi epsilon naught m r cube into x. We can compare this with our general equation. A is equal to omega square x. So omega will be equal to square root of q by 4 pi epsilon naught m r cube, or time period will be equal to 2 pi by omega, or that will be equal to 2 pi square root of 4 pi epsilon naught m r cube by q cube. This much depth questions they may not ask in NEET level, but in JEE you can expect this kind of questions. Now, electric field, this is the next application. Electric field due to long charged conducting cylinder. Long charged conducting cylinder. So as it is conducting cylinder, charge resides only on its surface. So infinitely long means we don't know its initial point as well as final point. We are considering one such cylinder with surface charge density sigma, where sigma is the surface charge density. So if we consider a point P outside, if its radius, cylinder radius is R, and we are considering a point at a distance R, here we will construct a Gaussian surface of length L and radius R. So now what is charge associated with that Gaussian cylinder means charge enclosed will be equal to sigma into curved surface area of the cylinder. What is curved surface area of the cylinder? That is enclosing charge means 2 pi RL. So now if I apply Gauss law, from Gauss law, this is at a point outside we are speaking, integration of E bar dot ds bar will be equal to Q enclosed by epsilon naught, or E into 2 pi RL will be equal to sigma into 2 pi RL by epsilon naught. So here we can cancel 2 pi L, 2 pi L. So we'll get electric field at any point outside is R epsilon naught. So you can expect some proportionality based questions. E is inversely proportional to R. If they asked on the surface means R will be equal to R. So electric field will be equal to sigma by epsilon naught. So it is a constant near the surface of the conducting charged cylinder. At a point inside, if they ask, at a point inside, as it is a conducting cylinder, overall charge will be distributed only on the surface. So if we construct a Gaussian surface inside, electric field, electric charge enclosed will be 0, Q enclosed is 0, so that flux will be 0 and hence electric field will be 0. So we can draw one graph also like this. At any point inside it is 0, outside inversely proportional to R. This is a graph between electric field and distance due to infinitely long charged conducting cylinder. So now electric field due to infinitely long non-conducting charged cylinder non-conducting charged cylinder. So as it is a non-conducting charged cylinder, charge is distributed throughout the volume. Charge is distributed throughout the volume. So here we will discuss with volume charge density. So if we are having one infinitely long charged cylinder, we are considering a point inside as well as outside. So first outside point. So if we construct a Gaussian surface, again we are considering the same dimensions. Its radius is r. We are considering a point at a distance r. If we construct a Gaussian surface, then charge enclosed will be equal to, if its length is L, density into volume of that cylinder. So volume of the cylinder will be equal to 4/3 pi r square L. So this will be charge enclosed by that cylinder. So now if I apply our Gauss law, integration of E bar dot ds bar will be equal to Q enclosed by epsilon naught. As it is surface area, we have to take only curved surface area, that will be equal to rho into 4/3 pi r square L by epsilon naught. So from this, electric field will be equal to pi r square h or pi r square L, will not get 4/3. So from this electric field will be equal to rho into pi r square L by 2 pi r L epsilon naught. So L gets cancelled, pi gets cancelled. We left with rho r square by 2 epsilon naught r. So here also electric field is inversely proportional to r. And if they asked on the surface, r will be equal to r. So that electric field will be equal to rho r by 2 epsilon naught. And if they asked at any point inside, they asked for an inside point. So here to construct a Gaussian surface whose radius is smaller, so that charge enclosed will be equal to density into volume of that cylinder pi r square L. And then if I apply our Gauss law, integration of E dot ds will be equal to Q enclosed by epsilon naught E into 2 pi r L will be equal to rho into pi r square L by epsilon naught. So pi gets cancelled, r gets cancelled, L gets cancelled. We'll get electric field as rho r by 2 epsilon naught. So that at any point inside, electric field is directly proportional to r, and outside it is inversely proportional to r. So that we'll get a graph like this. or variation of electric field with respect to distance for infinitely long cylinder non-conducting. So E is directly proportional to R and E is inversely proportional to R. Next we'll discuss about electric field due to conducting charged sphere. Conducting charged sphere. So as it is a conducting charged sphere, charge will reside only on its surface. Here also we have to consider only surface charge density. Here also we'll have three cases. That first case is a point P outside, a point P outside. If we construct a Gaussian surface over here, it will enclose complete charge. So charge enclosed will be equal to total charge. So if I'll apply our Gauss law, integration of E dot ds will be equal to Q by epsilon naught, or E into surface area of that Gaussian surface as it is cylindrical in nature, Q by epsilon naught. So electric field will be equal to 1 by 4 pi epsilon naught Q by R square. This is at a point outside. If suppose they are asking on the surface, R will be equal to R. So electric field will be equal to 1 by 4 pi epsilon naught Q by R square. And if suppose they asked at a point inside, for an inside point, charge enclosed is 0 and hence electric field will be 0. So if we draw a graph between electric field and distance, inside it is 0, outside it is inversely proportional to R square. This kind of questions you can expect based on a conducting charged sphere. Next we'll have non-conducting charged sphere. Electric field due to non-conducting charged sphere. That means charge will be distributed throughout its volume. So if we consider a point outside, for outside as it is enclosing complete charge, just like our previous derivation, there will be no big difference. Electric field at any point P outside will be 1 by 4 pi epsilon naught Q by R square. On the surface, electric field will be equal to 1 by 4 pi epsilon naught Q by R square. At any point inside if they ask, so here we have to construct a Gaussian surface inside, so that charge enclosed with that Gaussian surface will be equal to charge per unit volume into volume of that portion. 4/3 pi gets cancelled. So Q enclosed will be equal to Q R cube by R cube. This is charge enclosed. So and hence if they asked for electric field, that will be obtained from the help of Gauss law. Integration of from Gauss law, integration of E bar dot ds bar will be equal to Q enclosed by epsilon naught, or E into surface area of cylinder or a sphere, it will be 4 pi r square, will be equal to q r cube by r cube epsilon naught. So we can write like this: electric field will be equal to 1 by 4 pi epsilon naught q r by r cube. So this is electric field at a point outside due to a non-conducting charged sphere. At any point inside, it is directly proportional to, and outside it is inversely proportional to r square. At the center, it is 0. So this kind of questions we can expect, and then we'll have infinitely charged non-conducting sheet as well as conducting sheet. Electric field due to infinitely long charged sheet So if you are having one infinitely long charged sheet like this, let sigma be the surface charge density. So if I consider a point P which is at a distance r, if I construct a Gaussian surface, I can observe a similar kind of point on the other side also. On the curved surface of this, electric field and area vector are perpendicular. On the end caps, electric field and area vector are parallel. We are having two such end caps with surface area S, and at this point the charge enclosed will be equal to sigma into area, sigma into S. So that if I apply Gauss law, we have to take only end cap areas, because here curved surface area is perpendicular to electric field, so flux is not contributed with that curved surfaces, no contribution of electric flux. So integration of E bar dot ds bar will be equal to Q enclosed by epsilon naught. So E into two surfaces we are having, so that it will be sigma into S by epsilon naught. So electric field will be equal to sigma by 2 epsilon naught. So which is independent of distance. This is independent of distance. Independent of distance. And this is for a non-conducting sheet. And if you are given a conducting sheet, I'll mention that as a note point. For a conducting sheet, we have to assume like this: combination of two non-conducting sheets. So if I divide this into two parts, this first part and second part are two non-conducting sheets. So electric field in this region, due to both 1 and 2, if it is positively charged, it will be directed away. So E1 and E2, and even here also they will be directed away, E1 and E2. Net electric field will be equal to E1 plus E2. So that will be 2 times sigma by 2 epsilon naught, or that will be equal to sigma by epsilon naught. And of course inside it will be 0. Electric field inside a conductor, whatever may be the shape, it will be 0. And one more note point here we are having: if they are finite sheets of circular shape they gave, they are given a non-conducting sheet like this, and they are asking at a point P which is at a distance x, and its radius is r, it is subtending an angle theta. then electric field will be equal to sigma by 2 epsilon naught into 1 minus cos theta. And if it is a conducting one, if it is a conducting one, then electric field will be equal to sigma by epsilon naught into 1 minus cos theta. So you can expect some questions also based on this. That's it for this video. With this, I'll conclude a chapter called Electric Charges and Fields with detailed explanation. So you can follow other videos also. Nearly 7 to 8 videos are posted on this chapter. Just once go through each and every video, maintain a detailed notes so that you can solve all those questions very easily based on this. In this next video, I'll solve all those questions which are there in NCERT as examples as well as exemplar questions which are important for JEE as well as NEET. Have a great time. Please subscribe and share profile Progressive Physics Learning.